So there are 4 coulombs per second. But if you're wondering, how do you know that 4 amps is actually 4 coulombs per second? This is also on the AP Chemistry Equations and Constants sheet. So if you take a look, you can connect 4 amps to seconds by realizing that 1 amp is equal to 1 coulomb per second. So if I have 4 amps, I have 4 coulombs per second. But I have to put the seconds on top and the coulombs on the bottom. So I did 4 coulombs for every 1 second. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 9.10 and 9.11. As you can see on this slide, these topics fall under Unit 9 in the AP Chemistry curriculum, Thermodynamics and Electrochemistry. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 9.10, cell potential under non-standard conditions. Here are some essential knowledge statements from the AP Chemistry course and exam description. In a real system under non-standard conditions, the cell potential will vary depending on the concentrations of the active species. The cell potential is a driving force toward equilibrium. The farther the reaction is from equilibrium, the greater the magnitude of the cell potential. Equilibrium arguments, such as Le Chatelier's principle, do not apply to electrochemical systems because the systems are not in equilibrium. The standard cell potential, which has that symbol capital E with a superscript 0, the standard cell potential corresponds to the standard conditions of Q, the reaction quotient, equal to 1. Now, as the system approaches equilibrium, the magnitude, that is the absolute value of the cell potential, decreases, reaching 0 at equilibrium where the reaction quotient Q is equal to the equilibrium constant K. Deviations from standard conditions that take the cell further from equilibrium than Q equals 1 will increase the magnitude of the cell potential relative to the standard cell potential value. On the other hand, deviations from standard conditions that take the cell closer to equilibrium than Q equals 1 will decrease the magnitude of the cell potential relative to the standard cell potential. And in concentration cells, the direction of spontaneous electron flow can be determined by considering the direction needed to reach equilibrium. Algorithmic calculations using the Nernst equation are insufficient to demonstrate an understanding of electrochemical cells under non-standard conditions. However, students should qualitatively understand the effects of concentration on cell potential and use conceptual reasoning, including qualitative use of the Nernst equation to solve problems. So you can see that the Nernst equation is listed on the AP Chemistry Equations and Constants sheet in the section entitled Thermodynamics and Electrochemistry, and Q represents the reaction quotient, which is a ratio of products over reactants, as you can see in the equilibrium section. So Q has the same format as the equilibrium constant K. The difference between Q and K is that Q is the conditions that we have right now under a particular set of concentrations, where K would be the system at equilibrium. So we use Q in the Nernst equation, and we'll see examples of that in this lesson. All right, now it's time to move on to the practice for topic 9.10. And this is question 1, which begins with a diagram of a galvanic cell. So question 1 says the following. A standard galvanic cell is constructed according to the diagram above. The overall reaction that occurs in this cell is represented by the following equation. So we can see a balanced chemical equation, and it says under standard conditions, the standard cell potential is 1.63 volts. Now, a small amount of aqueous potassium carbonate is added to the lead half cell, and a white precipitate is formed. The observed cell potential changes slightly. Which of the following correctly describes how the cell potential is affected by the addition of aqueous potassium carbonate to the lead half cell and provides a valid justification? So what happened in this experiment is we began with a standard galvanic cell. We had standard conditions, but then a change was made, the addition of aqueous potassium carbonate to the lead half cell. And that change moved us into non-standard conditions. So now we have a non-standard cell. We can tell that these are non-standard conditions because as you look at the 4 answer choices for question 1, we can see that the cell potential is not equal to 1.63 volts. So under these non-standard conditions, we have to use our qualitative understanding of the Nernst equation to determine, will the new cell potential under these non-standard conditions be less than or greater than 1.63 volts? And will this change that was made to the lead half cell, the addition of the aqueous potassium carbonate, will this cause the reaction quotient Q to become less than 1 or greater than 1? So this is what happened. A small amount of aqueous potassium carbonate was added to the lead half cell and a white precipitate is formed. So I'm going to show in the diagram the addition of a little bit of that aqueous potassium carbonate to the lead half cell. A precipitate is formed. And so what we have to determine is whether that precipitate that is formed in the lead half cell will cause Q to be less than 1 or greater than 1. So under standard conditions, the concentration of the lead ions and the concentration of the gold ions would be equal to 1. So the value of Q is equal to 1 at standard conditions. Now, if you're wondering, how did I know to write the reaction quotient Q in this way? All I'm doing is the traditional setup for the equilibrium constant expression. Remember that we do not include solids in the equilibrium constant expression, but this is Q. This is not K, this is Q, the reaction quotient. So I've got concentration of lead ions raised to the 3rd power because of the coefficient of 3, and then divided by the concentration of gold ions raised to the 2nd power because of the coefficient of 2. So if the concentration of the lead and the gold is 1 molar, then the value of Q is equal to 1 at standard conditions. Here is the Nernst equation. And although that Nernst equation looks potentially confusing at first, all we really need to do is focus on a qualitative understanding of the Nernst equation. So the natural log of 1 is equal to 0. And when Q equals 1, then the cell potential is equal to the standard cell potential. In this case, that would be 1.63 volts. Now, if Q is not equal to 1, we have non-standard conditions. So the formation of that precipitate affected the concentration of the lead ions in that lead half cell. And so our job is to consider how is the value of the reaction quotient Q affected when a precipitate is formed in the lead half cell. Well, hopefully you can see that the formation of a precipitate would decrease the concentration of the lead ions in aqueous solution. And since lead appears in the numerator of the reaction quotient Q, and the concentration of lead is decreasing because of the formation of that precipitate, the value of Q is going to be less than 1. So if the value of the reaction quotient Q becomes less than 1, again, looking at a qualitative understanding of the Nernst equation, the natural log of a number that is less than 1 will be negative. Now, there is a negative in the Nernst equation, so a negative times a negative is a positive. So when Q is less than 1, this is what happens. If Q is less than 1, then the cell potential actually becomes greater than the standard cell potential because of the math involved. So natural log of a number less than 1 is negative. Negative times a negative is a positive. So the cell potential, when Q is less than 1, becomes greater than the standard cell potential. So at this point in our analysis of question 1, we know that the cell potential, when that precipitate forms, which causes the value of Q to become less than 1, will be greater than 1.63 volts. So the cell potential should be greater than 1.63 volts because the value of Q decreases. Now, here is that essential knowledge statement that confirms what's happening right now when Q is less than 1. Deviations from standard conditions that take the cell further from equilibrium than Q equals 1 will increase the magnitude of the cell potential relative to the standard cell potential values. And that's what's happening under these non-standard conditions here in question 1 in this packet. Now what I'd like to show you on the next slide is something that I will present at the end of this lesson as well. And this table presents a summary of both standard conditions and non-standard conditions that will help you understand how to answer these types of questions for topic 9.10, non-standard conditions. So, standard conditions: the concentration of the reactant is equal to 1 molar. The concentration of the product is equal to 1 molar. The value of Q is equal to 1, and the cell potential is equal to the standard cell potential value. But what if non-standard conditions exist that would cause Q to be less than 1? Well, you could either increase the concentration of a reactant, or you could decrease the concentration of a product. And that's what happened when that precipitate formed in the lead half cell. Lead ions are the product of this reaction, and the concentration of the lead ions decreased, causing Q to become less than 1. This takes the cell further from equilibrium than standard conditions, and the cell potential is greater than the standard cell potential. All right, let's go ahead and choose the correct answer to question 1. So we know that the cell potential should be greater than 1.63 volts, so I'm going to go ahead and eliminate choices A and B. And because Q is less than 1, that means that the value of the reaction quotient Q decreases. So the correct answer to question 1 is choice C. Now, we have another example of a non-standard cell in question 2. Let's go ahead and take a look at question 2. First, we have a diagram of a galvanic cell involving aluminum and zinc. So parts A and B of question 2 involve standard conditions. But then, when we get to parts C and D of question 2, that will move us from standard conditions to non-standard conditions. Let's go ahead and take a look at the details for the first part of question 2. It says a student sets up a standard galvanic cell with an aluminum electrode immersed in a 1 molar solution of aqueous aluminum nitrate and a zinc electrode immersed in a 1 molar solution of aqueous zinc nitrate, as shown in the diagram above. The standard reduction potentials for each metal are shown in the table below. Part A. Write the balanced net ionic equation for the reaction that occurs as this galvanic cell operates. Now, if you watched my last episode of AP Chemistry Review and Practice when I was teaching topic 9.9, cell potential and free energy, then you'll remember I used a strategy that I called the flip and add technique. And I will use that same flip and add technique right now to not only calculate the cell potential for this standard galvanic cell, but also to write the correct net ionic equation for the reaction that occurs in this galvanic cell. So what I have to remember is that the sign of the cell potential should be positive for a galvanic cell, and since both of these cell potentials for the half reactions are negative, I have to choose carefully which of these half reactions will I reverse. So if I choose to reverse the aluminum half reaction, then that cell potential will change from negative 1.66 volts to positive 1.66 volts. And then that will ensure that when I add the two cell potentials together for the half reactions, I will get a positive number for the overall cell potential for this galvanic cell. So I'm going to use the flip and add technique by leaving the zinc half reaction unchanged and then flipping or reversing the aluminum half reaction. So this is the reversed half reaction. I'm showing the electrons are now on the right instead of the left, and my cell potential changes from negative 1.66 volts to positive 1.66 volts. There's my zinc half reaction, which I did not change at all. But you may remember that when you add the two half reactions together, you need to get the electrons to cancel out on opposite sides of the equation. You also may remember that even though you multiply a half reaction by 2 or by 3, you do not change the value of the cell potential. So my coefficients for the aluminum half reaction will become 2, 2, and 6, but I did not change the value of the cell potential when I did that. For the zinc half reaction, I will multiply by 3. So I will not change the value of the cell potential for the zinc, but I will change the coefficients to 3, 6, and 3. And now you can see I can get 6 electrons on the left and 6 electrons on the right to cancel out. And so my overall balanced equation is 2 aluminum, solid, plus 3 zinc ions, aqueous, producing 2 aluminum ions, aqueous, and 3 solid zinc. Now the cell potential is positive 1.66 plus negative 0.76, and that gives me an overall value of positive 0.90 volts. So by using the flip and add technique, I have just answered parts A and B of question 2. So write the balanced net ionic equation for the reaction. It's going to be 2 solid aluminum plus 3 aqueous zinc ions to produce 2 aqueous aluminum ions plus 3 solid zinc. And the value of the standard cell potential would be positive 1.66 volts plus negative 0.76 volts, which gives me an answer of 0.90 volts. And again, that is a positive value, which is what you want for a standard galvanic cell. So now that we've answered parts A and B of question 2, we are ready to make that transition from standard conditions to non-standard conditions. Let's go ahead and take a look at parts C and D of question 2. It says that the student sets up a second galvanic cell using identical conditions to the first cell, except for making a change in the initial concentration of the aqueous zinc ions in the solution used in the zinc half cell as shown in the table below. So galvanic cell number 1, standard conditions, concentration of each ion is 1 molar. So Q, the reaction quotient, would equal 1 for galvanic cell number 1. But for galvanic cell number 2, where the concentration of the zinc has changed from 1 molar to 0.5 molar, the value of Q is not going to equal 1. So part C of this question says, calculate the value of the reaction quotient Q for galvanic cell number 2 at the moment that the cell begins to operate. Now, just like I showed you in question 1 of this packet, let's go ahead and write the expression for Q as products over reactants. Remember that we do not include solids in the Q expression, so it's going to be the aluminum ions on top and the zinc ions on the bottom. So the value of Q looks like this. Concentration of the aluminum ion squared because of the coefficient of 2, divided by the concentration of the zinc ion cubed because of the coefficient of 3. If I plug in a 1 molar for the concentration of aluminum and a 0.5 molar for the concentration of zinc, I can calculate the value of the reaction quotient Q for galvanic cell number 2. And so when I pick up my calculator, it's going to be 1 squared divided by 0.5 cubed. So 1 squared divided by 0.5 cubed, that gives me a value of 8. Now you may remember in question 1, the value of Q was actually less than 1. But here in question 2, this particular non-standard cell, the value of Q is greater than 1. So you might be thinking, how will the value of the cell potential be affected if Q is greater than 1? Well, that's exactly what we have to answer in part D of question 2. Based on the value of Q calculated in Part C, is the cell potential for galvanic cell number 2, again, that's a non-standard cell, is it going to be less than, greater than, or equal to the value of the standard cell potential that we calculated in Part B? Well, we know it's not going to be equal to, because this is a non-standard cell in which Q is not equal to 1. But is it less than or greater than 0.90 volts? There's our Nernst equation. We're using our qualitative understanding of the Nernst equation. What happens if Q is greater than 1? The natural log of 8 is going to be a positive number. And there is a negative sign in the Nernst equation. So what that means is that when Q is greater than 1, the value of the cell potential will be less. So not greater, but actually less than the standard cell potential. When Q is greater than 1, the cell potential is less than the standard cell potential. So there's that essential knowledge statement. Deviations from standard conditions that take the cell closer to equilibrium than Q equals 1 will decrease the magnitude of the cell potential relative to the standard cell potential. And that summary table that I had shown you earlier, I'm going to show you this again, but this time we're moving from standard conditions to non-standard conditions that take us closer to equilibrium than standard conditions. So what happened? Did we increase the concentration of a product? No, we actually decreased the concentration of the reactant. So zinc, the concentration of zinc was decreased, and zinc happens to be a reactant in this net ionic equation. So by decreasing the concentration of the reactant, that caused Q to become greater than 1, and the cell potential became less than the standard cell potential. So the answer to part D of question 2 is the following. The cell potential for cell number 2 should be less than 0.90 volts because the value of Q is greater than 1. All right, well, in this packet, we have one more question that deals with non-standard cells. Let's go ahead and take a look at question 3. Now, in question 3, it says that a standard galvanic cell is constructed with solid copper and solid zinc with a standard cell potential of 1.10 volts. A second standard galvanic cell is set up with conditions identical to the first cell, except that the solid copper electrode has a larger mass than the solid copper electrode used in the first galvanic cell. Now, this is not a change that we have seen before in this video lesson. In questions 1 and 2 in this packet, we looked at changes to the concentration of the ions, which can affect the value of Q, but we have not considered what happens if we change the mass of the solid electrode. Now, if you watched my previous episode of AP Chemistry Review and Practice, then you may remember seeing a copper-zinc standard galvanic cell. So on this next slide, I'll just show you, this was question 8 from episode 30 of AP Chemistry Review and Practice. And so the equation for this zinc-copper galvanic cell is listed in the center portion of this slide. So I'm showing you that it's the standard galvanic cell involving zinc and copper, and so there's my net ionic equation. Now the question asks, do you predict that the measured cell potential in the second galvanic cell, remember that all we're doing is we're changing the mass of the copper electrode, should it be less than, greater than, or equal to 1.10 volts? Justify your answer. Now if I write the reaction quotient Q, it's going to be concentration of zinc divided by concentration of copper. And that's it. Remember that we do not include solids in the Q expression. So concentration of zinc divided by concentration of copper, hopefully you can already tell that since solids are not included in the expression for the reaction quotient, then changing the mass of the solid electrode will have no effect on the cell potential. So here is my answer to question 3. If the solid copper electrode has a larger mass, this does not affect the value of the reaction quotient Q. Changing the mass of the electrode has no effect on the value of Q and would have no effect on the measured value of the cell potential. So therefore, is it going to be less than? No. Is it going to be greater than? No, it's actually going to be equal to. So the measured cell potential in the second cell should be equal to 1.10 volts. All right, well, questions 1, 2, and 3 in this packet dealt with topic 9.10 involving non-standard cells. So now it's time to move on to the review for our last topic in Unit 9, and that's topic 9.11, electrolysis and Faraday's law. Here is an essential knowledge statement from the AP Chemistry course and exam description. Faraday's laws can be used to determine the stoichiometry of the redox reaction occurring in an electrochemical cell with respect to the following: the number of electrons transferred, the mass of material deposited on or removed from an electrode, as in electroplating, the current, the time elapsed, and the charge of ionic species. Now, there is an equation which does appear on the AP Chemistry equations and constant sheet, and that's I, capital I, which represents the current, and the units of current are amps or amperes. You have the lowercase q, which refers to the charge, and that has units of coulombs. And you have lowercase t representing the time in seconds. And so now it is time to move on to the practice for topic 9.11. This is question 4. In question 4, we see a diagram for an electrochemical cell, but there's an important feature of the diagram for this electrochemical cell here in question 4 that is very different than the diagrams that you saw in questions 1 and 2 in this packet. So in questions 1 and 2, those diagrams represented a galvanic cell. But here in question 4, this diagram represents an electrolytic cell. It's the presence of that external power supply that tells you this is very different. This is not an electrochemical cell that can produce its own electrical energy like a battery. In fact, the external power supply tells us that this reaction is not thermodynamically favored, and that the overall cell potential for the reaction that occurs in an electrolytic cell is going to be negative, a negative cell potential. I'm just mentioning that the cell potential is negative, so you can see it's going to be different than a galvanic cell. Okay, let's go ahead and read the details of question 4. It says, molten lead bromide, which has the chemical formula PbBr2, is electrolyzed using an external power supply and inert electrodes as represented in the diagram above. Liquid lead metal and bromine gas are produced according to the equation shown above. The reduction half reactions related to the overall reaction in the cell are given in the table. So in part A of question 4, it says calculate the minimum value of voltage that must be applied for the electrolysis reaction to occur. So back in the earlier questions where we did that flip and add technique, I was trying to get for a galvanic cell the overall cell potential to be positive. But since this is not a galvanic cell, this is an electrolytic cell, I want the overall cell potential to be negative. Not positive, but negative. That is going to help me decide which of these half reactions I should reverse or flip. Another clue is that I need Br2 to be a product of this reaction. So we were given that Br2 or bromine gas is produced. So let's go ahead and leave the lead half reaction unchanged. Let's go ahead and flip the bromine half reaction to get Br2 to appear as a product. And now watch what happens when we add these two half reactions together. We're going to get a negative cell potential for the overall reaction. So because I flipped the bromine half reaction, that will change the cell potential from positive 1.07 volts to negative 1.07 volts. Half reaction, the one I did not reverse or flip, that remains as negative 0.13 volts. The electrons will cancel out. I see 2 electrons on the left, 2 electrons on the right, and my overall balanced equation is what we were given. And we have a cell potential that is negative 1.20 volts. So now we have answered part A of question 4 in this way. Based on the fact that the overall cell potential for this thermodynamically unfavored reaction is negative 1.20 volts, then the minimum voltage that is needed for this reaction to occur is 1.20 volts. So the answer to part A is the following. Calculate the minimum value of the voltage that must be applied for the electrolysis reaction to occur, and that's negative 1.07 plus negative 0.13. That's negative 1.20 volts. So the minimum voltage needed for this reaction to occur is 1.20 volts. As we move on to part B of this question, we will see the calculations involving the stoichiometry of this reaction. Let's go ahead and take a look at part B of question 4. In part B, it says if the current in the cell is kept at a constant 4 amps or 4 amperes, how many seconds does it take to produce 3.00 grams of liquid lead at the cathode? Now, the number that I see besides 4.00 amps is 3.00 grams. I'm going to begin with 3.00 grams of lead. If you're wondering, what about the 4 amps? I will use that as a conversion factor a little bit later, since I have to calculate the amount of seconds or time in seconds. But for right now, the first conversion factor that I will use comes from the information on the periodic table. I'm going to convert grams of lead into moles of lead using the information on the periodic table. So the atomic mass or the molar mass of lead is 207.2. So there's 1 mole of lead for every 207.2 grams. Now the next conversion factor will connect moles of lead to moles of electrons. But if you look at the overall balanced equation for this reaction, you don't see any electrons in the overall balanced equation. Well, that's because we canceled out the electrons on opposite sides. So I'll remind you that we had 2 electrons that were lost in the bromine half reaction, and we have 2 electrons that were gained in the lead half reaction. So for every 1 mole of lead that is produced in this overall balanced equation, there are 2 moles of electrons. So my next conversion factor looks like this. 2 moles of electrons on the top and 1 mole of lead on the bottom. Now what I have to do is consult the information on the AP Chemistry equations and constant sheet, because I have to connect moles of electrons to coulombs of electric charge. So there's the Faraday's constant. 96,485 coulombs of electric charge for every 1 mole of electrons. I will make the conversion factor with moles of electrons on the bottom and 96,485 coulombs of electric charge on the top. So remember that I said 4 amps. Well, how will I use 4 amps as a conversion factor? It turns out that 4 amps would be 4 coulombs for every 1 second. So there are 4 coulombs per second. But if you're wondering, how do you know that 4 amps is actually 4 coulombs per second? This is also on the AP Chemistry equations and constant sheet. So if you take a look, you can connect 4 amps to seconds by realizing that 1 amp is equal to 1 coulomb per second. So if I have 4 amps, I have 4 coulombs per second. But I have to put the seconds on top and the coulombs on the bottom. So I did 4 coulombs for every 1 second. Now when I pick up my calculator, I can convert from grams to moles for lead. I can convert moles of lead to moles of electrons. I can convert moles of electrons to coulombs of electric charge. And I can convert coulombs of electric charge to seconds. So it's going to be 3 divided by 207.2 times 2 times 96,485 divided by 4. And if I do all of that math, I get 698 seconds, and that's my answer to part B of question 4. And this is a good example of topic 9.11. Now, there are 2 more questions that remain in this packet, and they are also good examples of topic 9.11. Let's go ahead and take a look at question 5. In question 5, we also can see, based on the diagram and that external power supply, this is not a galvanic cell. This is an electrolytic cell. So it says in question 5 that an external direct current power supply is connected to 2 platinum electrodes immersed in a beaker containing 1 molar copper nitrate, aqueous copper nitrate, as shown in the diagram above. As the cell operates, solid copper is deposited onto one electrode, and oxygen gas is produced at the other electrode. The two reduction half reactions related to the overall reaction that occurs in the cell are shown in the table below. So in part A of question 5, it says write a balanced net ionic equation for the electrolysis reaction that occurs in the cell. Considering that we need solid copper to appear as a product, I don't think I'm going to flip or reverse the copper half reaction. But we do need oxygen gas to appear as a product, so it is likely that we will have to reverse the oxygen half reaction. So I will show you another example of that flip and add technique. Let's leave the copper half reaction unchanged. Let's go ahead and flip or reverse the oxygen half reaction. So there is my reversed version of that half reaction, so I can get oxygen, O2, to appear as a product. Now I will write the copper half reaction, and before we can add these two half reactions together, I need to get the electrons to cancel out on opposite sides of the equation. So what I will do is I will multiply the copper half reaction by 2, so I can get 4 electrons to appear on the left. So I'm going to multiply by 2. My coefficients will become 2, 4, and 2. And now I can get 4 electrons on the left, 4 electrons on the right to cancel out. When I add these two half reactions together, I can see that the overall balanced equation for the electrolysis reaction that occurs in this cell looks like this. We have 2 water plus 2 aqueous copper ions. And on the right side of the equation, we have oxygen gas, O2. We have 4 H plus aqueous ions, and we have 2 solid copper. So there is a balanced net ionic equation for the electrolysis reaction that occurs in this cell. Let's go ahead and move on to part B of question 5. Again, we will deal with the stoichiometry calculations for topic 9.11. So this is part B of question 5. It says calculate the average current in units of coulombs per second that must flow through the cell to produce 1.25 grams of copper in 1,680 seconds. Now, back in question 4, we calculated the time. So here, we're not calculating the time, we're actually calculating the current, and I need the units to be coulombs over seconds. So the first thing I will do is what I had done back in question 4. I'm going to start with grams, and I will convert from grams into moles. So I'm going to write down 1.25 grams of copper. I will use the information on the periodic table to convert from grams to moles, and there is 63.55 grams of copper for every 1 mole of copper. The next thing I will do is convert from moles of copper into moles of electrons. And if you're not sure about moles of electrons, remember that for every 1 mole of copper that is produced, there are 2 moles of electrons. Now, you also could say 4 moles of electrons for every 2 moles of copper, but since the ratio of 4 moles of electrons over 2 moles of copper, that reduces to 2 over 1, I'm just showing you the reduced version, and you would get the same answer if you had 4 over 2. Now, if I stop right now, I've got moles of electrons, so again, I will consult the information on the AP Chemistry equations and constant sheet involving the Faraday constant. So there's 96,485 coulombs of electric charge for every 1 mole of electrons. Remember that in part B of question 5, we need the current to be in units of coulombs per second. So if I do the math right now, I would get coulombs. I need coulombs per second. So my last conversion factor will be seconds on the bottom. So I've got 1 over 1,680 seconds. And now if I pick up my calculator, the grams of copper will cancel out. The moles of copper will cancel out. The moles of electrons will cancel out. And I will have units of coulombs on top and seconds on the bottom. So it's going to be 1.25 divided by 63.55 times 2 times 96,485, and then finally divided by 1,680. So the answer to part B of question 5 is 2.26 coulombs per second. You also could write 2.26 amps, but amps and coulombs per second, those are equivalent units. So there's my answer to part B of question 5. We have one more example of topic 9.11, and that is question 6. Let's go ahead and take a look at question 6 in this packet. And you can see, looking at the diagram in question 6, it's another example of an external power supply. So an electrolytic cell, not a galvanic cell, but an electrolytic cell. So question 6 talks about an electroplating experiment. Here are the details of question 6. An electroplating experiment is performed in which a bronze coin is immersed in a solution containing a substance that's an aqueous ion that contains gold. The chemical formula is Au parentheses CN4, and it has a negative charge. Now that ion is in solution. Electricity is passed through the solution, and a thin layer of solid gold, and you can see that solid gold appears on the right side of the equation. A thin layer of solid gold is deposited onto the surface of the coin according to the reaction represented by the equation shown above. A constant current of 5 amps is applied to the cell for a period of 925 seconds. Now, back in question 4, we calculated the time in units of seconds. In question 5, we calculated the current, which had units of coulombs per second. So what are we doing in question 6 that's a little different in terms of our calculations? Well, in question 6, we're actually calculating the mass. So it says calculate the mass of solid gold that should be deposited onto the surface of the coin during the experiment. So I'm not going to begin with grams. I'm actually going to end with grams in my calculation. So what I'm going to start with is time. So the first thing I will do is I will write down 925 seconds. Then I will use 5 amps. So 5 amps is 5 coulombs per second. But I have to write that 5 amps as a conversion factor. So it's going to be 5 coulombs on top and 1 second on the bottom. Now if I stop right now, I've got coulombs, but I need to connect this to moles of electrons. So here comes the Faraday's constant one more time. It's going to be 96,485 coulombs for every 1 mole of electrons. Don't forget that we have a balanced equation in which 3 moles of electrons are featured as a reactant and 1 mole of solid gold is featured as a product. That tells me that for every 1 mole of gold that is produced, it involves 3 moles of electrons. So my next conversion factor looks like this. 1 mole of gold for every 3 moles of electrons. I'm only 1 step away from calculating the mass of solid gold. I'm going to use the information on the periodic table, and that tells me that for every 1 mole of gold, it's 196.97 grams of gold. Again, I'm converting from seconds to coulombs, from coulombs to moles of electrons, from moles of electrons to moles of gold, and then finally from moles of gold to grams of gold. So I'm going to pick up my calculator, 925 times 5, divided by 96,485, divided by 3, and then finally times 196.97. And so when I do that math, I get 3.15 grams of solid gold is produced in this experiment. All right, well, now that we have the answer to question 6, which was the last question in this packet, it's time to move on to the part of the lesson where I give you advice to help you avoid common mistakes. My first piece of advice is that if you need more information about topics 9.8 to 9.11, you can review the information in my video, and there's a link to that video in the video description area. My next piece of advice is to read the question carefully and make sure you are answering the question that is being asked. Always show your work for your calculations, and as I mentioned earlier in this lesson, you can use the following guidelines to compare the voltage of a non-standard cell to the voltage of a standard cell. Assume that all reactants and products are either aqueous or solids. Let's start with standard conditions. The concentration of the aqueous reactants and products would be 1 molar. The value of the reaction quotient Q equals 1. And at standard conditions, the cell potential is equal to the standard cell potential. So what happens if you let this standard galvanic cell just run over time? Well, what happens is that as the galvanic cell runs over time, the concentration of the reactant decreases, the concentration of the product increases, and the cell potential decreases. So eventually, you reach equilibrium, where the concentration of the reactant is a very small number, the concentration of the product is a very large number, and the value of the reaction quotient is equal to the equilibrium constant K, which is typically a very large number. But when the cell reaches equilibrium, the cell is dead, and the cell voltage becomes 0 at equilibrium. But as you can tell, in between standard conditions, where Q equals 1, and equilibrium, where Q is a very large number equal to K, we have non-standard conditions. Now there's non-standard conditions that take the cell further from equilibrium than standard conditions, and there's non-standard conditions that take the cell closer to equilibrium than standard conditions. Let's go ahead and consider both of those non-standard conditions. So, if there are deviations from standard conditions that take the cell closer to equilibrium than Q equals 1, then this will decrease the magnitude of the cell potential relative to the standard cell potential. So that's highlighted on this slide. So if Q is greater than 1, you are now closer to equilibrium, where the cell goes to die, than standard conditions. And if Q is greater than 1, the cell potential is less than the standard cell potential. On the other hand, if you have deviations from standard conditions that take the cell further from equilibrium than Q equals 1, then this will increase the magnitude of the cell potential relative to the standard cell potential value. So that's highlighted on this slide on the far left. If Q is less than 1, then now you are further from equilibrium than standard conditions, and the cell potential is greater than the standard cell potential. So again, this is a diagram that's a good summary of these non-standard cell conditions that will help you with answering questions involving topic 9.10. And with respect to topic 9.11, the following relationships are used in calculations involving Faraday's law. We have current is equal to charge over time. So that's I equals Q over T, and the units of amps are coulombs per second. We also have the Faraday constant, so 96,485 coulombs for every 1 mole of electrons. And then finally, what about the number of moles of electrons for every 1 mole of a particular substance? You can use the half reaction if you know it, or the equation for the overall reaction to identify the correct relationship between moles of electrons and moles of a particular substance in a redox reaction. So here are 4 examples. We have silver, zinc, and aluminum, and those are listed as half reactions. So there's 1 mole of electrons for every 1 mole of silver. There's 2 moles of electrons for every 1 mole of zinc. There's 3 moles of electrons for every 1 mole of aluminum. Now the last one's a little more tricky or challenging because what you're looking at the bottom of that table on this slide is a overall balanced equation. You don't see the electrons actually listed in that equation, but they were present in the half reactions that were added together. So it turns out that there are 4 moles of electrons for every 1 mole of oxygen gas that's produced, or you could say 12 moles of electrons for every 3 moles of oxygen gas, O2. So just remember that if you are working a problem involving topic 9.11, where you're doing these types of calculations, make sure you get the correct conversion factor that will connect the moles of a particular substance in the redox reaction with the number of moles of electrons. Okay, so we have come to the end of this lesson. In my next lesson, I will do some comprehensive AP Chemistry exam review to help you get prepared for the AP Chemistry exam. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which includes the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.